All right, we can go ahead and get started. Today we have Shuai with us, who's going to be doing his PhD talk. Shuai joined UTIG, the Polar and Planetary Geophysics group, in 2017 after getting a bachelor degree in geophysics from the University of Science and Technology of China. His PhD thesis is focusing on studying subglacial hydraulic networks in East Antarctica using geophysics data and aiming to understand how it evolves and interacts with the overlying ice sheet. He's done a lot of field work in Antarctica in his time here, and he's also joined multiple geological and geophysical field campaigns around China during his undergrad, and did 3 months of surveying in Antarctica during his time here at UTIG. And now he's going to tell us about all that. So take it away.
Thank you, Aaron. Yeah, super excited to do this talk. Let me turn on the laser pointer. Cool, yeah. As promised in the title, I want to tell a story about lakes under ice sheet, how we discovered those lakes and how we derive more information about them. And before that, I want to do a quick acknowledgement. I'm very fortunate to have a very supporting group here at UTIG and also co-workers from institutes all around the world. And it is their help and support that made all the work I'm about to show you possible. So I'm very grateful for their help. So the title of this talk is Airborne Geophysical Survey over a Subglacial Hydrology Network in Princess Elizabeth Land, East Antarctica. So there are 3 key components of the title. One, airborne geophysical survey. Second would be sub-ice hydrology, and third would be Princess Elizabeth Land, East Antarctica. And that's how I designed this talk. So I want to first do a very brief, simplified introduction to the concept of subglacial hydrology, and then I will do a quick walkthrough of our survey method, and then I will show a few examples in PEL East Antarctica. And I want to show the key takeaway points before the talk, so that if you're in a rush and have to go now, you won't feel guilty. But yeah, it's my hope that with those key takeaway points in mind, it'll be easier for you to follow my logic, and it'll be easier for you to see the whole big picture. So the first thing I want to show is that we have this new data set which fills in the biggest coverage gap of the current version of our basotopography database. And from this new dataset, we identified a widespread hydraulic network beneath the ice sheet in East Antarctica. And one of the newly identified lake, it probably hosts a very, very valuable sediment record of the environmental changes and ice sheet changes in the past. So let's dig into the details. Here's a graph that I created with all my art skills. Yeah, I want to demonstrate the basic idea of subglacial hydrology. So most of Antarctic ice sheet is grounded, i.e. is sitting on a bedrock, sitting on the Antarctic continent. So if you zoom out, that would be the big picture you see, right? But if you zoom in, and if you zoom into the interface between the ice sheet and the bedrock, in certain locations, you will see a layer of water. And they are there for a couple of reasons. First, of course, you have this geothermal flux, the heat coming out from the bedrock. And there's a frictional heat due to the flow of the ice sheet. And because ice sheet is not a very good thermal conductor, so the bottom of the ice sheet is essentially isolated by itself from the cold atmosphere, right? And of course, there's pressure melting effect. So altogether made it possible for water to exist beneath the ice sheet. So here's a more beautiful graph, a more comprehensive demonstration. A few things I want to point out here is that those lakes beneath ice sheet, they come in different sizes. There are bigger ones, because they're bigger in size, it takes them longer to drain and fill, so they tend to be more stable, as shown here, stable lakes. The existence of water will reduce the basal friction, and when the area of the water is big enough, that impact on the ice sheet dynamics will have a signature on the surface. So that impact is big enough to propagate all the way through to the top. So sometimes you can see this surface flattening over those water. And those big lakes, some of them have a layer of sediment preserved at the bottom of the water. And those sediment could provide a very valuable record, and that could predate any of our ice core record we currently have. And speaking of ice core record, if you think about the old ice preservation, hydraulic condition is a very important factor in that equation, because at least thing you want for your ice core site is to have melting constantly happening at the bottom, right? Those valuable old ice being melted away. And of course, there are some smaller ones. Normally they locate near the coastal region where the ice flow is faster. And because they're smaller, they tend to be more active. They drain and fill on a shorter period of time. And one thing I want to point out is that some of the water drain will eventually end up in the coastal area where we have those vulnerable ice shelves. So those water may become essentially discharged toward the bottom of those ice shelves and regulating the basal melting and stability of those ice shelves. So sometimes we see in the news report about, an ice shelf of the size of New York City just collapsed and all the ice volume was dumped into the ocean. And subglacial hydrology, those water discharge may be one of the factors deciding whether or not that happens or how frequent that happens. I guess the point I'm trying to make here is that whether you care about the past, i.e. ice core record or sedimentary record, or you care about the future, i.e. Ice sheet dynamics, ice shelf, or sea level rise, subglacial hydrology has something to offer. And this research front has been very active in the past 50 years or so. This graph shows the frequency of the words subglacial lake and subglacial hydrology being mentioned in public literature. And you can see this huge jump in the past about 50 years, a very significant increase in the interest and effort that went into this research front. And one of the reasons is that as we know more about the ice sheet dynamics, the more we realized, yes, indeed, this research front is a very important part of the equation. Another reason is we have seen a very significant advance in technology that went into this research front. For example, here, around 1968, we had the first ever radar sounding over Lake Vostok, which is the biggest lake underneath Antarctic ice sheet. And so it's the first direct observation of the water. And that just opened the door to a whole new world. And UTIG has been a very active contributor in this research front. Just to name a few, we have multiple former UTIG PhD students that focused their PhD dissertation on this research topic. And of course, there has been many publications from UTIG researchers. So you can imagine those phrases, those terms pops up in conversations all the time in our UTIG building. And one of the ways we contribute to this research front is through our geophysical observation. So the big idea is we put some scientific instruments on an aircraft, and we turn them on, and the aircraft will fly through our interested area so that we have data points along the flight path, along the survey path. So here is a typical configuration of our survey platform. The instruments were installed on a BT-67 aircraft. And you can see we put skis on the wheels of the aircraft so that it can take off and land on the surface of the ice sheet. We have radar sounders beneath the wings of the aircraft. And so the radar is pointing downward. So it constantly shoots out signal and here for reflections. And we have a magnetometer on board sticking out of the tail of the aircraft. Beneath the belly of the aircraft, we have an altimeter and optical camera. And we have multiple GPS devices on board. And within the cabin of the aircraft, we have a GT2 gyrometer and a whole support system for that. Because those types of gyrometers, they require a very specific working condition, working temperature, and as you can imagine, it is not a very easy thing to do when you are flying 4,000 meters above sea level in Antarctica. So we built a whole support system for that gyrometer, and all the instruments, they are controlled by a central integration system. So essentially we will have a integrated data set. So what can we get from such surveys? Here is a typical radar figure we would get. So you can imagine it as a cross section of the ice sheet. So on the top would be the surface of the ice sheet, and in the bottom we have bedrock. So the first reflection we get is the reflection from the surface of the ice sheet, and the very last one normally is from the bedrock. And between those two endpoint reflection, we get multiple reflections from within the ice volume. And they are a very valuable record of the past dynamics condition of the ice sheet. They are like a history documentation of what has happened to the ice sheet. And sometimes in the basal reflection, we see this flat, bright, shiny reflection, and that's an indicator for the existence of water. So to distinguish water from bedrock in our radar survey, we rely on 3 key criteria. The first one is hydraulic potential. It's a potential energy caused by gravity and the pressure from the ice sheet. And for the water to be stable, this potential energy has to be constant across the whole water body. And the next one is basal reflectivity. Basically is how much energy can be reflected back toward our radar sounder. And the third one, and of course, water would have a much higher reflectivity than the rock. And of course, the third one is specularity, which basically describes for a certain amount of reflection energy, how much of it is directly toward the right angle and how much of it is scattered to all the other angles. And my favorite quote on this one is from my advisor, Don. He once said, just imagine a mirror versus a carpet. You shine your light on a carpet, the whole room is lit up. But if you shine your light on a mirror, only very specific part is lit up. In that case, mirror has a much higher specularity than a carpet. And so the same for water. Water would have a much higher specularity than the surrounding rock. So to identify water, we need to see a constant hydraulic potential or a zero hydraulic slope. And we require high reflectivity and specularity. And sometimes we see spots with high reflectivity, but the specularity is not as high as we would expect for water. And that's indicator for sediment beneath the ice sheet, water saturated sediment. Here's an example of using this method to identify water. You see almost zero hydraulic slope. It's not absolute zero because of course, our radar instrument is not perfect. There's a certain level of uncertainty on the surface elevation measured and the basal topography measured. So there's a certain tolerance for that. And we see high reflectivity and really high specularity. And also we see the spot with high reflectivity and low specularity, which is which is sediment around the water. So that's radar. And when we also have gravity anomaly measured, and we can do an inversion on that anomaly and get a lot of different information, say density of the bedrock. And if there's water, we can estimate how thick the water is. And if there's sediment, then we can put that sediment layer into the inversion model and get an idea of how thick the sediment is. And here are some examples of using this method. Flynn et al., a former UTIG PhD student, she used gravity inversion plus seismic observation and built a 3D bathymetry model for Lake Vostok. And I used the same method for another location. I'm about to show that in just a minute. And that work was accepted a few weeks ago by Geology, and we are now wrapping up the production stage. So the paper should be out in either next week or the week after. So yeah, new paper alert. And of course, we have magnetic, which can be used to get some idea about the geologic context. Here are some examples from Grunch and Hudson et al. So they calculated the magnetic response of some very simplified geologic structure. And this article is a very nice review, and they have a whole list of different scenarios. So if you're interested in this method, I would say this paper is probably a good place to start. So I hope by now I have given a very quick walkthrough of our survey method. So next, as promised, I will tell you a story about how we use this method in Princess Elizabeth Land, East Antarctica, PEL. So PEL is this sector of East Antarctica sitting within Amory Ice Shelf and West Ice Shelf, two of the major ice shelves in East Antarctica. It's right next to Mountain Gambarziv and Dome A, where some study has proposed that this location is where East Antarctica ice sheet initiated. And the ice thickness currently in PEL is up to about 4,000 meters. And we don't have any data. We didn't have any data up until a few years ago. So on the right is the data coverage map of BADMAP 2, the current version of BADMAP. BADMAP is a database for basal topography and ice thickness. So if you do, say, reconstruction of the ice sheet behavior in the past, or do predictions about the ice sheet behavior under this warming climate, you probably have used this database for multiple times. So in this data coverage map, the dark markers are the previous survey passes. So that's where we had data. And the kernel code represent how far it is from the nearest data coverage. And as you can see, PEL, we simply didn't have any data when this database was put together. So it's a very critical gap in our data coverage. We had no idea about what is going on beneath the surface of the ice sheet. But we did have a quite decent observation of the surface of the ice sheet from satellite. And that is where this story started. So when going through the satellite imagery, Jimison et al., they noticed this extensive feature on the surface, a feature of topographic depression. And that feature extends all the way from the interior PEL toward the coastal region. And they propose this is actually a signature of a canyon network covered by the ice sheet. And they did have a few survey passes near the coastal region, and that confirmed this hypothesis as shown in this graph. Excuse me. So after examining the location, the shape, and the orientation of this proposed canyon network, they proposed that this canyon network was initiated by certain tectonic events before Antarctic glaciation. So it was born before Antarctica was covered by ice sheet, and it was born as a subaerial river channel. So the river drainage probably have cut the channel deeper, and then when ice sheet finally came, glacial erosion probably have cut the channel even deeper. And in the upstream part of this proposed canyon network, they observed this flat, smooth feature on the surface of the ice sheet. And they proposed this is a signature of a major lake beneath the ice sheet, because that's what we normally see for such water bodies beneath the ice. And so here, for example, here is what the surface of the ice sheet looks like over Lake Vostok. You can see this big, smooth and flat feature right above Lake Vostok. And back in the days, aviation pilots, they used to use this feature for navigation purposes. So there's a permanent station nearby, and the pilot would just use this feature. Because it's so big, you can't, even you are flying hundreds of meters above it, you can't miss it. Assuming that's the same case for PEL, this signature on the surface of the ice sheet could indicate a very major new lake in this region. So when we put all that together, PEL is a very significant reservoir of grounded ice. It's next to two major ice shelves, and there is probably a canyon and lake system beneath the ice sheet. And all I have just said was not confirmed because we didn't have any data when this paper was published confirming all the hypotheses, right? So we have all the big hypotheses waiting for confirmation by more direct measurement. So that motivated our group to do geophysical observation in this region. And we have been sending people to Antarctica every winter in the past a few years. And after spending multiple Christmas and New Years with penguins and seals, we now finally have a very decent coverage, data coverage in this region. Here are the survey passes we did in the past few years in PEL East Antarctica. And there has been already a few papers that came out from this work. Here is a new basal topography map of PEL published by Cui et al. In 2020. So now we fills in the biggest gap of our previous database. So this new work is going into the next version of BATMAP, BATMAP 3, which our group at UTIG is a very active contributor as well. So my thesis focusing on using this new dataset to study the hydraulic condition beneath ice sheet. So with this new observation and rely on the three criteria I just talked about, we confirmed, yes, indeed, there is a very big water body beneath the ice sheet. So we confirmed the existence of this lake among other smaller ones. You can see almost zero hydraulic slope, very high reflectivity, at least 15 dB higher than the surrounding region, and a very high specularity. And we gave this lake a name, Lake Snow Eagle. It's named after the aircraft we used to do most of the survey here. So we're just trying to address her contribution here. And in the background, you can see her twin sister, JKB. So Lake Snow Eagle is about 40 kilometers by 15 kilometers. And around Lake Snow Eagle, we see those spots with high reflectivity, but not very high specularity. And we suggest that's the sediment reflection. So essentially you have a pot of water sitting within a sediment column. And of course, in the more downstream region, we identified a few more lakes. And when putting all the locations together with the location of the proposed canyon network, we can sort of see this correlation. And one of the ongoing project of mine is to look at this correlation and figure out what does it mean for the ice sheet throughout glacial cycles. And because we have the most dense data coverage over Lake Snow Eagle, for the rest of the talk, I will use it as an example to demonstrate how we can further study the properties of such lakes. So here's a radar-derived surface elevation of Lake Snow Eagle. The gray solid marker are the survey passes. And you can see this depression, topographic depression on the surface of the ice sheet over Lake Snow Eagle, which agrees very well with our satellite observation, right, where the story started. And that is just a proof that the existence of water of such size indeed has impact on the surface, on the ice sheet dynamics, and that impact is strong enough to propagate all the way to the surface of the ice sheet. And I want to point out that, because it's in Antarctica, the north direction normally is not what you normally see. So in this map, the north direction is toward the right-hand side. Here's a basal topography map. It's very obvious that Lake Snow Eagle is sitting in a subglacial channel. So we confirm the existence of this proposed canyon channel, at least in this part of PEL. Here's a free air gravity anomaly. And you can see this very short wavelength anomaly, negative anomaly over Lake Snow Eagle, which is what we expected, right? That's caused by the density difference between water, sediment, and bedrock. And we can do a quick inversion for that and estimate how thick the water is and how thick the sediment is. So we did that, and here's the result. On the left-hand side is a few cross sections of our inversion models. And when we interpolate those profiles together, we get the water thickness map and sediment thickness map on the right. Because it is interpolated from separate profiles, this map essentially is a conservative estimation of the water volume and sediment volume. And of course, we have magnetic anomaly shown here. And you can see this, there's a very strong negative anomaly on the west shore of Lake Snow Eagle. And there are two very strong positive anomalies, one on the northwest shore and one on the eastern side of Lake Snow Eagle. And when you put the magnetic anomaly and the basal topography together, there's not a strong correlation between those two, right? And that suggests that all the anomaly we see in the magnetic map probably is caused by some changes within the bedrock instead of the surface of the bedrock. So there may be some sort of geologic discontinuity going on within the bedrock. And we want to figure out what type of discontinuity is that. So we did a few inversion for the magnetic data, and we did that for multiple profiles across the lake. Shown here is one of the profiles. So here is a cross section, and on the top you have the calculated response in red curve, and the dark dot are the actual measure. Oh, so there's somebody knocking on my door. Sorry, give me 1 minute.
I'll take this moment to say this is a PhD talk. If you want to fill out the Google form that I put in the chat, it goes towards picking the best PhD talk at the end of the year, which they get a prize for. So I'll put that in the chat again.
Yeah, I'm back. I'm so sorry. Somebody knocked on my door, and I'm sorry. I'm so sorry about that. All right, let's get back into the talk. Yeah, we did a few inversions, and because we don't have any direct observation of the geology, we tried to keep the models simple, right? So we build the models based on 2 different assumptions. Setup number 1 assumes that the geology looks like something with a magnetized bedrock capped by a non-magnetized cap unit. Setup number 2 assume, the bedrock is overall non-magnetized, but there are a few magnetized strata within the bedrock. And for both setups, the models with compressional geologic features gave a much better match than the models with extensional geologic feature. So altogether, they indicate the existence of a compressional geologic boundary over Lake Snow Eagle region. So from that inversion, we estimated the location of 2 thrust faults in this region. So what do we know? What do we know so far? We have water on top of faults, and there could be hydrothermal circulation going on along the fault plane, which would bring up more heat toward the bottom of the ice sheet from the bedrock. And that could induce enhanced basal melting because of the existence of this geologic framework. And we want to confirm that hypothesis, because if confirmed, that could be at least one of the sources of those water here, right? If not the major source. And that would have some implications for sediment analysis as well, because there are certain dust and particles sealed in the ice volume, and when the ice finally melts, those particles will be released, and eventually they will be deposited toward the bottom of the water. And to confirm this hypothesis, right, we look at our radar measurement, because again, it's like a historic documentation of what happened and is happening toward the ice sheet. We traced multiple reflections within the ice volume, and we calculated the normalized elevation. Basically, it's the elevation of the reflection normalized by the thickness of the ice sheet. So if there is basal melting, we would see all those layers, all those reflections being drawn down to the bedrock. So we did that, we did some calculation, and that is exactly what we see. These are the normalized elevation for each individual reflections, and bright yellow color represent negative anomaly, which means the layer is being drawn down to the bottom of the ice sheet. And we can see this short wavelength negative anomaly over Lake Snow Eagle, which is an indicator for basal melting in this region. So we have enhanced basal melting. And as you can tell, most of the water and sediment sit in the deeper northern basin, which means there is enhanced erosion in the northern basin. And that's exactly where we propose those two faults in the bedrock. So enhanced erosion possibly associated with the geologic context. So the water is there, possibly because of this geologic framework, and the water stopped there because this deep basin, because of this geologic framework. So altogether, essentially, it suggests a overall geologic control of such subglacial lakes. So that's about the water. Now let's talk about the sediment. We see a very thick sediment layer preserved beneath Lake Snow Eagle. Typical sediment thickness is over 100 meters, and maximum is over 300 meters. And the big question is, what information does this sediment column archive? Right? If one day we could get a sample from this sediment layer, what information can we get from that core? So there are a few possible sedimentation sources listed here by the order of time. The first one would be pre-glacial fluvial, because again, the canyon network, the host channel of Lake Snow Eagle, is proposed to be born before Antarctic glaciation and is served as river channel. So there might be a layer of fluvial sediment there. And of course, when Antarctic glaciation came in, during the initiation and growth of the ice sheet, there could be this effect called glacial buzzsaw, which basically when the ice cap initiated on the top of the mountain, there will be a significant erosion on the mountain, which will produce a very large amount of sediment. And those sediment could be transported and preserved at Lake Snow Eagle. And of course, under glacial conditions, there could be sediment brought by the ice sheet and brought by subglacial hydraulic activities. Either this slow fill and drain of water or this sudden outburst, those subglacial flood. Of course, there's a time limit on the late 3 sedimentation process, because Antarctica has only been covered by ice sheet for about 36 million years. So there's a time limit on the last 3. And there's another time limit for the last 2, because it would require hydraulic activity going on beneath the ice sheet, right? So that's a time limit. But and we need to know how fast is the sediment being deposited, but we don't have any direct measurement of the concentration of dust in the ice and so on. So I borrowed some numbers from Lake Vostok. Felina et al. Estimated the rate for different sedimentation process over Lake Vostok, and assuming that the rates are at least on the same order here, we can borrow that number and get a very general idea of the structure of the sediment layer. But again, there's time limit on the last 2, and we don't know how far back in the time it is, right? If you give those last 2 sedimentation process enough time, they could contribute a very major portion to the sediment column. But say if Lake Snow Eagle is very young, for only a few thousand years, then those last 2 sedimentation process probably only contribute to a very thin layer on top. So we need to know how old Lake Snow Eagle is. To do that, again, we look at the history documentation, the radar figure, right? And in the ice column right above Lake Snow Eagle, in the upper portion of the ice sheet, we see this very irregular stratigraphy. Normally, what you see in radar is those reflections, they go up and down over topography, but they're sort of parallel to each other. But that's not what we see at all here in the upper portion of the ice sheet over Lake Snow Eagle. You can see those reflections, they are not parallel to each other at all. The thickness of the ice layer between those reflections varies a lot. So it's this very irregular stratigraphy we see in the ice sheet over Lake Snow Eagle. And it is a very short wavelength anomaly. It's about the same scale as Lake Snow Eagle and is only observed in the upper portion of the ice column, right? So what could cause this type of irregularity? Well, there are a few suspects here. There could have been some change in climate forcing. There could have been some sort of reorganizations of the ice flow. And of course, there could have been some change in the subglacial geologic condition, which probably triggered some basal melting or freezing, and that will have a signature on the stratigraphy as well. And of course, you could have certain hydraulic activity going on beneath the ice sheet, and that impact might propagate all the way to the top and had a signature on the surface slope, which when that surface slope finally became an in-glacial reflection, you can still see that signature there. So they are all possible suspects, but some of them may have some argument that they are not guilty, right? The first two, they would leave a much large footprint. They will have a much longer wavelength signature, because when you have this climate change or the large scale reorganizations, their signature will not be isolated and limited in a 50 kilometers long region. And the third one and the fourth one would have impact on the entire ice column, right? The whole column would be drawn down if you have basal melting. So after ruling out the first four possible causes, we have this irregularity is possibly caused by certain hydraulic activities beneath the ice sheet. So if we can somehow figure out how old this irregularity is, then we can estimate the age of Lake Snow Eagle, right? So let me repeat that. Because this irregularity is supposedly associated with the existence or the activity of Lake Snow Eagle, then if we know the age of this irregularity, then we can have at least first order estimation of the age of Lake Snow Eagle. And very fortunately, we have an ice core site nearby, which is connected by survey passes to Lake Vostok and then eventually to PEL and to Lake Snow Eagle region. And we have multiple dated reflection in this ice core site. So in the past few months, I extended those dated reflection into our new database, and shown here marked as blue a few of those dated reflection. One is about 10,000 years old, another one 38,000 years old, and another one over 33,000 years old. And we can see this irregularity is sitting right above that 10,000 years old reflection, right? Which means that irregularity is probably younger than 10,000 years old, which argue that Lake Snow Eagle is quite young. It's younger than 10,000 years. So when we put that number back, and let's be generous, let's give Lake Snow Eagle 10,000 years, and let's give Antarctic ice sheet 40 million years, because again, we're only looking for the first order estimation, right? And when you put that number in, that will only give you about 3 meters of sediment. So unless the sedimentation rate here at Lake Snow Eagle is 30 or 50 times higher than Lake Vostok, which is not very possible. Those sediment column, a major portion of those sediment column would be from periglacial sedimentation process. So if one day we can get a sample from the sediment layer, what we will see is something like this. In the bottom, we probably will have sediment deposited by periglacial processes, which can give us some very valuable information about what Antarctica is like before it is covered by ice sheet. In the middle portion, and probably the middle portion, is periglacial sediment, and that could provide some insight about how, where, and when East Antarctica ice sheet initiated. And of course, on top, there will be some sediment brought by the ice sheet and hydraulic networks beneath the ice sheet. So that would be a very valuable sedimentation record, and actually pretty cool, right? But it's only a starting point. There's definitely more work need to do. It'll be great if we can have some seismic surveys over this region so that we can have a better understanding of the structure of the sedimentation sediment column. And if we can have more data coverage here, then we can do a more sophisticated 3D inversion. And it'll be great if we can have some numerical modeling of how the water circulate within the lake, so that we know how the sediment was redistributed when they arrived at this location. And finally, we will be ready to do some drilling and coring. So again, to sum it up, we have this new data set that fills in the biggest coverage gap of our current basal topography and ice thickness database. And from that new data set, we identified a widespread hydraulic network beneath the ice sheet. And among those newly identified lakes, the biggest one, Lake Snow Eagle, potentially hosts a very, very valuable sediment record of how the environment changes and how the ice sheet changed in the past. So that's all I want to show in this talk. Yeah, again, I'm sorry about the interruption earlier, and I'm happy to take any questions.
Awesome job. Thank you, Shuai. If anyone has any questions, feel free to unmute yourself, or you can post them in the chat and I can read them as well.
Shuai, this is Don. I got a quick question about the 34 million years. Did you actually look at where Lake Snow Eagle is with respect to that paper that Duncan wrote about the fjord evolution over to the east in Aurora Basin? I'm a little confused about whether it's on the side where the ice sheet's only 14 million years or the side where it may be up to 34 million.
We lost your audio, Don. Is that all the question, or? Oh,
test. Am I still in there?
Yeah, we can hear now.
Oh, okay. Yeah, I'll ask the question again. Yeah, the 34 million years, you know, the existence of the ice sheet. PEL is over on the highland, you know, that that should be impacted by it's on the west side of the highland that complements the east side of the highland, where Duncan wrote the paper about the fjordization. And then he had an idea about where things should only be about 14 million years of, you know, of ice covered time, and where things should be more than that. Where's PE? Did you look at that from the perspective of where Lake Snow Eagle is?
Let me pull out that map here. So next look is here, right? If my memory is correct, is that proposed location either somewhere here?
Highland A and Highland B.
Highland B is somewhere here.
Yeah, and the boundary is down by Shackleton Ice Shelf, so it's over to the east of west.
It's on the east side of PL because PL is here and this is east. Yes.
Yeah, so the logic he used for separating what was 14 million years old and what was 30-ish million years old could be applied over on this side too. I just wonder if you did that.
Not yet. But yeah, it's definitely on the to-do list because yeah, that would definitely make a difference because that's about 50% difference.
Yeah, anyway, I just thought that that would be fun.
Yeah, yeah, definitely. That will make a difference. But again, we are looking in this talk. I'm just want to show the first order estimation. So I didn't go in too much detail into that.
That's all good. I know it's the last paper.
Right. Another question. So this PL is kind of weird in that there's really no active lakes in this area, the ones that go pop up and down and are seen in the satellite altimetry. Any, apart from one at right near Emery Ice Shelf, any speculation on why that might be?
Good question. Yes, the first thing is we don't see any active lake right now. I know there's currently a work going on in our among our collaborators in Shanghai. They are looking at satellite imagery over the past few decades to look at whether that argument is true or not. But yeah, if that argument is true, and indeed we don't see a very active hydrologic network in this region, a possible argument would be there's not a significant melting rate to support the activities. Another one is I look at this drainage analysis by Jamison et al. Back in 2016. I don't know if that's the most up to date, but the drainage network essentially around Lake Snow Eagle is not connected toward the coastal region. Probably that's because they didn't have that accurate measurement of the geometry of the canyon network in their model. But assuming that's true, what my understanding is that those water essentially is sort of trapped. So it's not essentially connected hydrologically toward the coastal region.
Thanks. I think Natalie might have a question in the comments.
Yeah, Natalie asked, how is subglacial sediment usually sampled?
Good question. It's not easy thing to do, especially in Antarctica where we want to preserve the environment. And we also want to preserve the ice sheet itself, right? It's not only just, breaks through the ice, there are multiple different drilling methods, hot water and cleaning drill, or essentially mechanical drilling. And I know there is currently work being proposed to drill Lake Snow Eagle because, again, our work proved that this may be a very interesting site and valuable site for such work. But I don't see that happen in the next at least 5 years because there's a lot more work to do before that. Yeah.
Got a couple minutes left for another quick question or something. All right, then. It's always fun to see work that, has some component of active collection where you get to go somewhere and actually take data. So thank you, Shuai, for your
Thank
talk.
you.
We've got one more next week by Natalie Wolfenbarger. Feel free to come back. See y'all.
Thank you, everyone. See y'all.